Hello, in this video I'm going to run through the usual diagram that's used to describe the standard model. Now, this doesn't describe the entirety of the standard model. I mean, that's a very complicated thing, a lot of which is way beyond what we're going to be looking at. Is getting into quantum mechanics and all the rest of it, which is beyond the scope of these videos. But it's useful to look at the diagram that's used to describe the particles that are within the standard model, because it starts bringing us into the terminology of what all these particles are called and why they're grouped in certain ways. If you think back to the previous video that we had, where I was saying that these fundamental particles are observed by physicists in the laboratory, they see how they behave, and then different behaviors are given different descriptions, which are then said to be the properties of these fundamental particles. And they've all got names, and we need to know what those names are so we can talk the language of the standard model, the language of particle physics. So the first thing I want to mention before I draw the diagram is we do have a distinction to make between matter and antimatter. So most of the universe, I mean, when I say most, pretty much all of it, is made of a certain type of matter. But there's also antimatter, which is sort of the shadow reflection, the mirror image of this matter. So taking an example of antimatter, we know that we've got matter. There's a lot of electrons in matter. Every atom has got electrons orbiting around the nucleus of that atom. And the antimatter equivalent of the electron is the positron. Now, we don't have positrons floating around all over the place, but the positron is identical to the electron in every way, except whereas the electron has got a negative electric charge, the positron has got a positive electric charge. Everything else is the same. We've just got this mirror image based on one property of the matter there. And that's the matter and the antimatter. Now, we're not including all of the antimatter inside this diagram that I'm going to draw here at a standard model. Now, you could do, because each fundamental particle has its antimatter equivalent, but it's just going to clutter up the picture. So, usually people leave these things out. But keep this in mind, and we'll come back to antimatter later on, because it does bring us on to something of a puzzle with the universe as to why there isn't more antimatter kicking about. But I'll leave that for another video. So I want to go through this fairly quickly so we can get an idea of all of the terminology and the distinctions involved. So let's make our first distinction based on one of the 5 key properties we spoke about in the previous video, and that is on spin. So on the left-hand side, I'm going to have particles with half integer spin. And on the right-hand side, I'm going to have particles that have got integer spin. Now, if you may recall from the previous video, we were saying if a particle has got half integer spin, it obeys the Pauli exclusion principle. So that means that it makes up solid matter. This is the stuff that we touch in the world around us, the things that we can pick up. So this is our solid matter from the Pauli exclusion principle, whereas the stuff on the right hand side isn't. So this is why it's a really key distinction. Now, these have got names. On the left hand side, we've got fermions. On the right hand side, we've got bosons. And again, I'll talk about where these names come from in another video when we're getting into this in more detail. I just want to get all of this out here now. So we've got fermions on the left, we've got bosons on the right. So let's have a closer look at fermions. We'll make another distinction based on another one of our fundamental properties. So does it obey the strong interaction or not? Does it engage in the strong interaction? So if it does engage in the strong interaction, we'll then put it right here on the left. And if it doesn't engage in the strong interaction, then we'll put it here on the right-hand side of this block. And if you remember again, we were saying that any particle that engages in the strong interaction has got color charge. and then if it doesn't, then it doesn't have color charge. And we've got two more names for these. So we've got quarks, which you've probably heard of, and we've got leptons. Quarks and leptons, they're all fermions. It's just the distinction about whether they engage in the strong interaction or not. And then we've got 3 generations of these, so it gets even more complicated. Generation 1, Generation 2, Generation 3, which are very similar to each other. The main difference, really, at least for us beginners here, is mass. We've got heavy ones at the bottom, lighter ones at the top, and the heavy ones decay to the lighter ones. So they're unstable at the bottom and they're more stable at the top. So you don't get Generation 2 and Generation 3 fermions just existing around in the world every day. These are things that we're creating in the lab in places like CERN. So what are these specifically? So Generation 1 quarks are our up quark and our down quark. Generation 1 leptons are our electron and our electron neutrino. Right, when we move up to Generation 2, we've then got the strange quark and the charmed quark. We've got the muon and the muon neutrino. Generation 3, we've got top quark, bottom quark, the tau and the tau neutrino. So we've got a certain pattern going on here. We've got these pairs of fundamental particles, but it's these top ones here, these ones, now Generation 1 fermions, that are making up pretty much everything that we see around us. This is the stuff that's making everyday matter, and that's where we're going to focus most of our attention throughout our videos on structure of matter. But we will have a look at some of the others as well, exactly what they are, what their properties are, you know, what sort of mass and charge and things like that, where their names came from. We'll look at those in other videos. But that's a breakdown of names and terminology that we've got on this side. One interesting point with this, if you think of the fundamental interactions. So leptons here, they've got no color charge. They're not involved in the strong interaction. So you can't bind 2 electrons together because there is no, you need the strong force, which is the most, has got the greatest magnitude of these interactions. You'd need that in order to overcome the repulsion from the electromagnetic interaction, which is driving these electrons apart. So, you know, 2 electrons, bring them together, the same electric charge will cause them to repel. So these are pushing each other away. The only way you could hold them together is if you had a stronger interaction that was pulling them together. Now, the only stronger interaction is the strong interaction, and they don't engage in that because, you know, we're saying they've got no color charge. So this is why we can't bind electrons together. Quarks, it's a different matter. Although you might have, you know, 2 quarks that have got the same electric charge, if you get them close enough together, because the strong interaction only operates over a very small range, but if you get them close enough together, they can bind together because that strong interaction has got, you know, so much greater magnitude, you know, 100 times the strength of the electromagnetic repulsion. So this is why quarks can bind together to form things like protons and neutrons, whereas leptons, they just hang around on their own. You know, you might be thinking, well, what happens if you put an electron and a positron together, because they're going to attract with these opposite electric charges? Well, they end up annihilating and they just turn into energy. So you can't even bind those together. Yeah, these leptons, they're hanging around individually here. So that's an interesting distinction that you've got there amongst the fermions. Right, let's come back to the right-hand side and look at our bosons with our integer spin so they don't take up space. These we're splitting into 2 groups again. We've got what's known as gauge bosons. These are also often called force carriers. These are the particles that sort of mediate these fundamental interactions. So if you've got two fermions that are interacting in some way, then they interact, which is an exchange of energy and momentum, and that is mediated by this particle, a gauge boson, which is said to be transferred from one fermion to the other fermion, which is what's transferring this energy and momentum across. So each interaction has a gauge boson. So the electromagnetic interaction, that's mediated by photons. So that's our electromagnetic. The strong interaction mediated by gluons, that's strong. The weak interaction is mediated by the W and Z bosons, so that's for weak. And then we've got the bit of a sticking point with the standard model of, well, what's going on with the gravitational force or interaction. As I mentioned in the previous video, our best description of that is in general relativity. If you were going to bring that into the standard model, we'd want some gauge boson that's going to mediate this. You know, people talk about the graviton, but this is just sort of speculated. We haven't got any actual experimental evidence for one of those, but that would be the gauge boson that would mediate the gravitational interaction. So we've got this collection here of force carriers of these gauge bosons. And there can be a lot of energy in these bosons. You know, don't just ignore these things because they're not taking up space. You know, we're going to look at this more closely later on, but the mass of macroscopic objects, you know, including ourselves, if you add up all the quarks that are inside us, all the quarks and the electrons that make up all the atoms inside us, then that doesn't get us very close. You know, that's only a small percentage of the total mass that we have. So much, vast majority of our mass comes in the form of comes from the energy that's holding these fundamental particles together. It's coming from the gluons in particular in the nucleus of each atom that makes us up and makes up all the other matter in the world. So there's a lot of mass sitting around in these force characters because there's a lot of energy here. So these are strong forces, these are strong interactions. So there's a lot of energy involved. So there's a lot of mass involved. Now, the other bosons, if it's not a gauge boson, is a scalar boson. And I've said scalar boson in the singular because we've got one very famous nowadays scalar boson, the Higgs boson. And I will do a video all by itself on the Higgs boson because it's become very popular since it was discovered not that recently. Yeah, we've got the experimental evidence now that the Higgs boson does actually exist, which was a nice feather in the cap of the standard model. It was predicted that this thing would be around, so they went out looking for it and they managed to find it. So I'll talk about that elsewhere. But that's where I'm going to leave it for the moment with the standard model layout. You can see that it's all built up on these distinctions: fermions versus bosons based on spin, solid matter versus non-solid matter. Then on the fermions, we've got strong force, not strong force, quarks versus leptons. On the boson side, we've got force carriers and knots. We've got the gauge bosons and the scalar bosons. So we've already got quite a lot of terminology thrown in here. But really, the ones that you're wanting to think about are the names of these gauge bosons, the names of these quarks and leptons, what the difference is between a quark and a lepton, and what the difference is between a fermion and a boson. And we'll keep unpicking all of this as we work through our structure of matter.